It's a pleasure to have our first distinguished lecture at AI2 Emerald Landing facility, and I can't think of a better person to inaugurate it than Pedro Domingos, who's an old friend and colleague, and more importantly, he's really one of the deepest thinkers in machine learning today, spanning both practice, winning a bunch of KDD Cups, theory, winning a bunch of awards, and most recently he won what's called the Nobel Prize for Data Science, really just like, was a week or two ago.
Yeah.
So, Pedro Domingos.
Well, thank you all for being here. Please feel free to ask questions at any time. So I'm going to talk about, this is probably the longest, I realized as I was preparing these slides yesterday that this is probably the longest title of any talk I've ever given. I don't know if that's a good or a bad sign. It's probably a good sign. Probably means there's a lot of content. So the talk is going to be about extracting knowledge from text with tractable Markov logic and symmetry-based semantic parsing. And this is work that I've been doing at UW with Austin Webb, Matthias Nippert, and Chloe Kidden. And of course, you know, they've done all the great stuff, and I get to take all the credit, as usual. A warning, this is mostly work in progress. So this is stuff that is not very mature yet, but I thought it would be more fun and more interesting to talk about some of the more speculative directions that we're working on. So what you'll see is going to be mostly ideas, some formal results, and some theoretical and some experimental results, you know, thrown in for good measure. So here's the roadmap. This talk is basically going to have two parts. One, as the title implies, one on tractable Markov logic and one on symmetry-based semantic parsing. But we'll see how they both contribute to the same goal, and at the end how they connect. So here's a little bit of motivation to get things started. Although I think for you guys, the motivation that I'm going to give probably doesn't need belabored much. We want to solve AI. Solving AI requires a lot of knowledge. This is really the big bottleneck. The important thing that that really prevents us from getting there is acquiring a lot of knowledge. And the easiest way to acquire knowledge is by reading, right? However, doing that is hard. On the one hand, text is very rich, so that knowledge is there if we can somehow get it out. But text is extraordinarily messy. It's variable, it's ambiguous, things come in many different forms, it's very noisy, there's missing, I mean, it's a mess. So if we want to extract knowledge from text, right, and then we want to have the computer reason with it, that knowledge needs to be in some formal language. And that language, I think, needs to be relational because text is rich. Right? A propositional language isn't going to cut it. You're not going to be able to express the kinds of things you want to. And it has to be probabilistic because since the text is very messy, the result is also going to be messy, right? There's no way we're going to clean up everything and produce a beautiful, pristine first-order knowledge base or something like that. Unfortunately, both relational and probabilistic on their own lead to intractable inference, let alone when you combine them. So what can we do? Well, we certainly have languages that are expressive enough that encompass both of these things, like Markov logic, which I've worked on for the past 10 years. But we want to build large knowledge bases, very large knowledge bases. And we want to reason with it very reliably and very quickly. And doing that in a language like Markov logic, most of the time is going to be very hard. So maybe one thing that we can do is come up with a language that is tractable. So it's tractable. So it's going to have all that, all those nice properties that we want in terms of scaling up and being well behaved, but still expressive enough. Okay. And now, of course, this is the circle that we're always trying to square in AI, is between tractability and expressiveness. But what we're going to see here, or at least what I hope to convince you of, is that this language that I'm going to describe, called tractable Markov logic, is a new trade-off between expressiveness and tractability. Actually, until a few years ago, I would have thought was impossible. So I wouldn't have thought we can have this amount of expressiveness and this amount of tractability at the same time. Having said that, it still doesn't do miracles, so it's not going to be the complete solution. But I think we can get a lot of mileage out of something like this. So what is tractable Markov logic? Well, the basic idea is that it's a probabilistic version of semantic networks, object-oriented systems, default logic, people know these things by different names. But in essence, what tractable Markov logic is a language where you can have 3 types of rules and 3 corresponding types of facts. The first type of rule is there is a hierarchy, right, in a semantic network, classes and subclasses. So for example, I can have a rule like, is family social unit, which says that families are social units, and this rule is going to have a weight that corresponds to the probability that a social unit is a family as opposed to something else. And then we can also just have plain, instance facts like the Smiths are a family. Okay? So this is a hierarchy, and of course we're also going to have the is part or has a hierarchy. And now we're going to have rules of the form, for example, has family adult 2, which is saying that every family contains 2 adults. So every object of type family has 2 subparts of type adult. And then we can have facts, just plain facts, and again, this is not necessarily a deterministic rule, right? Not all families necessarily have 2 adults. And then we can also just have plain facts like, for example, has Smiths an adult 1 means that in the Smiths family, the first adult is Anna, okay? And then finally, we have just relation rules and relation facts. Relational rules say things like, for example, in a family, every adult is a parent of every child. Okay? And again, sometimes parents are not, this rule is not perfect, right? The children might be adopted, or there might be children from previous marriages of the spouses or whatever. So again, this is going to have a weight that corresponds to how strong of a regularity it is. And in addition to that, of course, we can also just have plain relational facts, like, for example, Anna and Bob are married, or properties of the objects, like, how tall Anna is or whatever. Okay?
Why aren't subpart and subclass just instances of relations here?
Oh, very good, right? For the same reason, so the answer to a lot of questions like this is actually the same as in knowledge representation, which is they're special. They're going to play a special part in making difference tractable. At the level of first-order logic, right, these are all just relations, right? But the problem with first-order logic is that it's too expressive. So what's going to happen is that these 2 are going to have a particular structure. And it's like, just to give you a preview of what's going to happen is that condition on these are all going to become independent. So if I guarantee certain things on this that are fairly natural, as I hope to show you, then this becomes easy. So there's conditions on these, and they're sort of like what you might expect. There's a class hierarchy, there's a part hierarchy, et cetera, et cetera. Okay, so these play a special role is the answer to your question. Yeah.
I don't fully understand what the second and third argument means.
So here,
Yeah.
or in the rule or in the fact?
Well, the 2 facts, they seem to mean different things, the second and third argument. So I was.
No, yeah. So the rules and the facts have a different form. Okay, so this rule says that a family, so these rules basically say what are the subparts of objects of a certain class. So that rule is saying that objects of the class family have 2 subparts that are of class adult. You could say, for example, that objects of class platoon, right, have a subpart of class commander and a subpart, and 20 soldiers and 1 sergeant or something. Okay.
Actually, so those 2 things are completely different.
Yeah, so exactly. So they're completely different. And then what this is saying, this is a fact, is saying, well, okay, family has 2 adults, but who is the first adult of the Smiths? It's Anna. Right? So it's just basically going to tell you a bunch of facts about the world. Okay. More questions?
So these things, should I view these adult family Smiths as constants in first? Or are these like?
No, yes, yeah, exactly. So I'm actually not doing that here, but each of these can be mapped very directly into first-order logic statements. This is really all just a syntactic sugar for certain formulas in Markov logic that you can write.
And the same is true for the classes?
All of these, yeah. The same is true for all of them. So I mean, if you look at the AI 12 paper where we introduced this, there's a table that for each of these shows the corresponding Markov logic form, which is more cumbersome, but you can readily imagine how you would say any of these things in first-order logic. But then there's interesting additional conditions like, well, as we'll see shortly, that like the subclasses of a class are mutually exclusive. Since that's always true, I'm not forcing you to say that every time, which in Markov logic I would have to. You had a question?
I'll let you do the next one.
Okay. The question is whether you have a question. Okay, so this is the basic syntax. Now, of course, it's not just any old pile of things like this that will become a tractable knowledge base. So here are the restrictions that you have to have. And our compiler, you know, when you input this, it will check whether you've given us something correct or not. And these are that there's one top object, which is the universe, out of which all the other objects are subparts. Okay, we'll see an example of this shortly. You know, so you're doing molecular biology. Your top object could be, you know, the cell. It's a cell, or it could be an organism, which will then have cells as subparts and so on. And there's one top class, which is the class or the top class of the top object. Now, relations must be among subparts of some object, right? We're not going to allow arbitrary relations all over the map because that could very easily set up an intractable situation. They have to be subparts of some object, okay? Yep.
But they're all subparts of the top object.
Exactly, right? Thank you for anticipating that, right? So you can always, right? So I can always say, oh, well, you know, just you know, push this up to the top object, right? But you have to remember that and you know, we're going to see this in a little bit more detail shortly, right? But what these models are setting, what this is setting up is that the relations among the subparts of an object are independent given the class. So if you push them up to the top object, what you're saying is that, you know, they're all independent given the class of the top object. And if you do that with every relation, you'll basically just get an exponential blow up in the number of classes. So the whole game is that you actually want this to be done at the lowest level possible. And as long as your relations are mostly clustered among subparts, like, you know, most working relationships are within the same organization, and then a few of them are across organizations, then life will be good. If you have an arbitrary relationship of, you know, an arbitrary, you know, set of relations of the type works with or friends or something, then you're in trouble. Okay. It's not that you can't have it, it's that then modeling it will be very impoverished. You know, at the end of the day, you could always just have a big knife-based model at the level of the top object, right? But how much does that help you? Okay, that's a very good question. Subclasses are mutually exclusive. This is actually also fairly specific. And some of these things, by the way, they can be relaxed, and some of them we have relaxed them. But doing things this way makes life fairly simple. And objects do not share subparts. And let me just add one thought to this, which is my cognitive scientist friends actually tell me that these assumptions are very well known as assumptions that human beings tend to make. So you could argue that this is how we make the world tractable, is by, you know, making assumptions like this. Sometimes even when they're not quite true, but we treat them as being true. So maybe this is a natural set of assumptions to make. Okay? The goal here, by the way, is not to just have a tractable language, but to have a tractable language that is natural for people to state things in, and that is a natural match to the information that comes from text. Yeah?
So this was actually my question. The objects do not share subparts.
Sorry?
The objects do not share subparts, but it's always like transferring. So does that mean that, I've never understood, does that mean that the Anna who is the mother of the Smiths is not the same Anna that works for Microsoft, for instance? Is there any different?
Yeah, so very good. So another great question. Let's think of Anna as part of the Smiths and Anna as part of the company that she works for, right? So that could be a very big source of trouble. In some ways, this is one of the biggest restrictions that we're making here. I'm saying that in the same world, right, Anna is not part of both of these things at once, okay? And now actually, and you might say like, whoa, that is a very strong restriction. So let me relax it right away. And here's what happens, that I can actually have easily Anna be a part of both, as long as some of her properties depend on her as a member of the Smiths, but not as a, you know, someone who works for Microsoft. And some of her properties depend. So there's Anna the Microsoft worker and Anna the Smiths, you know, mother, right? So, you know, so that obeys this assumption because I actually have two objects, Anna 1 and Anna 2, okay? And, you know, depending on how you want to do syntactically, you can call it Anna. But if you allow Anna to be a member, if you allow properties of Anna to depend on, you know, multiple sets that she's a member of, then you potentially have trouble, okay? And again, you could argue that people do tend to make this distinction between, for example, the world of work and the world of home.
I don't agree with that. So if I want to say, does the mother of the Smiths family work for Microsoft?
No, actually, you can do that. Yeah, actually, that's a good example. You can do that because what happens is that, well, let us defer that question until we've seen more of the mechanics. Yeah, but you can actually answer a question like that, and in fact, we do. More questions? All right. If you write or you build from text a knowledge base, you know, in this form that satisfies these restrictions, then you set up a particular type of probability distribution over the possible worlds, meaning, you know, what objects exist and what classes they're members of and what properties they have and relations that exist among them and whatnot, right? So that was the syntax. We can check that it's correct when it comes in or make sure that you only produce things correct in that sense. But what does this mean? Okay? This defines a probability distribution. And the way that this probability distribution is defined is a little bit unusual. But you know, that's really where the tractability and the expressiveness come from. So let me define it in the following way. A probability distribution is really defined by its partition function, right? The partition function of a distribution is the sum of the probabilities of all states, right? If you give me the partition function, everything else follows from it, right? Like Richard Feynman famously said that statistical physics is the study of properties of the partition function. And here we're doing something similar for AI, perhaps. So let's see how the partition function is defined, and then we'll see how basically all the questions that you might want to answer, the usual marginal and MAP questions, will follow from that. And the way we're going to define the partition function is recursive. And this is different from what's usually done in a Markov network or a log-linear model or whatever, but that's where we get some of the power. So here's what I'm going to do. I'm going to define the subpartition function for an object class pair, and Z is the traditional letter to represent partition functions, comes from the German, as follows. It's going to be a product of three things. One has to do with the subclasses of C, one has to do with the subparts of X, and the other one has to do with the relations, the properties of X and relations among its subobjects and whatnot. So what are the three parts? The first part is just a sum. See, here I have the partition function for the same object, but for its subclasses. So I'm going to have is a sum over the subclasses of C, each weighted by E, to the corresponding weight. Okay. So you could think of it as like this is really the, a little mixture model, right, with the mixture components being the subclasses of the class. Okay. And now inside here I could have who knows what, right? I just recurse down, into the partition function for these subclasses of the same object. Okay. Here, what I have is a product over all the subparts of the partition function for that subpart and the corresponding class. Okay. And if I have many objects of the same, many subparts of the same class, then I can just raise it to that number. And this is a small example of lifted inference. Okay. So if a society, as we'll see in a short while, has 100 million families, I don't necessarily need to do things 100 million times. I do them once and I raise them to a power. Or I'll have to do them once for each subset that I have different evidence for, but that's the general idea. So this is the subpartition function for the, this is the component that has to do with the subparts. And finally, I have the component for the relations. And basically what happens, if you think of this as a probabilistic model and this is the latent structure, right? Like, for example, a clustering model, a mixture model would be a very simple instance of this. Once you have these guys all become independent. So relations only interact, and properties of objects only interact via the classes that they're part of. Okay? And so then once I have one of those relations in isolation, the partition function is very simple. It's just, so this just going to be the product over all the relations because they are independent, conditioned on where I am, of the two cases, which is if the relation is false, I get e to the 0, and if relation is true, I get e to its weight. Okay? So this is just as in the log-linear model or in Markov logic. Okay. So the subpartition function has these three parts, and notice that here I'm recursing down into subclasses, and here I'm recursing down into subparts, and here the recursion ends. Okay. And where does the recursion begin? Well, the partition function of the whole knowledge base is just the partition function of the top object in the top class. Okay. So the partition function of the top object in the top class basically captures the distribution over everything. Okay. And now if I want to answer a query, right, you can think of this in terms of the usual conditional or marginal questions, but also in terms of think of an AI knowledge base, and your query could be any formula, right? I want to know what is the probability that this formula holds, that, that Anna smokes given that she's friends with a smoker or whatever, okay? Well, that can just be done by basically computing all of these conditional, queries can just be done by computing the ratio of two partition functions. One is the partition function of the knowledge base with the evidence added to it, and the other one is the partition function of whatever that evidence might be, even if it's formulas, and the knowledge base with the query added to it. And we're going to see an example of this shortly. And the ratio of those two things is my probability. Okay? So so the bottom line is, if I know how to compute partition functions, I know how to answer all questions. Okay? Yeah.
I'm just having a hard time with an example of what's an object versus what's a class in this.
So the Smiths, for example, are an object, and family is a class. Okay? I'm going to show an example of this very shortly that hopefully will make things more concrete, both in terms of what TML is and of why it's tractable. Okay? So here's the punchline, however, is that you can prove that with distributions defined in this way, with the syntax and semantics, then the partition function of every knowledge base in TML can be computed in time and space polynomial in the size of the knowledge base. And in fact, roughly speaking, ignoring a few details that don't really matter, the time and the space of computing the partition function, and therefore any query, is order of the number of rules times the number of objects. And in fact, if you want to be even finer, it's really order of like the sum over objects of the number of rules that apply to it. Which means that this is very, very scalable. And in fact, in our implementation, we get that, we can answer queries over very large knowledge bases in a fraction of a second. And and compute real probabilities according to the to the TML knowledge base that was set up because of this. So this is not just tractable in a theoretical sense. It's actually something that scales up very, very well and can be done on knowledge bases. We can do things with many, many objects and rules in this way. Yeah.
Can you go back to the previous slide?
Mm-hmm.
So normally for the partition function, I would expect to see a big summation over all possible configurations, and I see that the relations just by multiplying them out. What's the independence assumption again that lets you do that, the last part?
Right, so notice where the summations are, right? So there's one here, and there's one here. And that's it.
I understand, but
what I've actually done is I've pushed that outer summation into these things here, right? So that's only a partial answer to your question.
And then this becomes like a sum product.
Oh, no, exactly. So your question is like, what are the dependence assumptions that are being made here? One I think very useful way to think about this is that this is setting up a sum product network. So the dependence assumptions this is actually why we can be more tractable than we previously thought was possible, is that this isn't going to have the simple kinds of graphical model independencies. A typical TML knowledge base, if you represent it as a graphical model, is going to be a big clique. It's going to be a huge mess. But nevertheless, the sum product network with context-specific independencies, right? There's going to be different independencies for different subclasses and so on, is going to be tractable. And I'm going to put up an example right after this of this. Okay? So let's see the example, right? I realize that this is sort of like a big pile of theoretical constructs, but let's try to make it more concrete now. So let's see a simple example of a TML knowledge base and why, right, it's tractable. Okay, so I'm not going to prove the theorem here, but I think I can give the intuition in a way that I hope will be fairly clear. So let's suppose that our top object is America. We want to build a model of America, right? And America is an object of type society. They could be different subtypes of society, but society is the top class and America is the top object. And in this very, very simple world, let's assume that America is composed of 100 million independent families. Of course, in reality, we want to say, well, America breaks up maybe into states and then into cities and neighborhoods and whatnot. But let's just go straight to the level of families. Okay. So what this means is that the model for America is going to be a product of the models for the individual families. The families are all independent, right? My model for America is just a product of one model for each of the 100 million families. So here, I have a decomposition of America into subparts. And those subparts become the children of a product node in the computation of the partition function or in the sum product network, if you're familiar with sum product networks. Okay? And now let's pick one particular family, the Smiths, right? Now the Smiths can have more than one class. They could be, say, a traditional, two-parent family, or it could be, a single parent, et cetera, right? But now, because I have choices over what Smiths could be, meaning I have notice what I've done from here is that like America has become a subpart, which is the Smiths. And here I still have Smiths, but now what I have is subclasses of family. Okay? And in this case, as you probably already expect, what I'm going to get is a sum. Because my model for America is going to be a product of the models of the families. My model for the Smiths is going to be the sum, the weighted sum of the model for the Smiths as a traditional family and the model for the Smiths as a one-parent family. Okay? And the mixture components, right, are just the exponentiated weights of the corresponding formulas. Okay? It actually pays, a brief parenthesis, to have these as weights and not as conditional probabilities, because that way we can basically build a default inheritance hierarchy where these things are just successive corrections. And when there's no correction, when you go from a class to a subclass, like as say from the probability of flying when you're a bird versus a penguin versus opus, you can actually leave it out, right? So this actually allows to build much more. It allows to have some of the traditional properties of inheritance hierarchies, except in a probabilistic model. Okay. So now the Smiths, can be a traditional family or a one-parent family. And now, of course, the Smiths decomposes into subparts, like, for example, Anna and Bob. And, now I'm going to have a product over that. And finally, I have relations, for example, like, let's say, Anna and Bob are married with, with a weight of 2.3, meaning with a non-normalized probability of e to the 2.3. And then the partition function for that is just that little sink that we saw there before, which is the sum of, e to the 2.3, which is the true case when they're married, and e to the 0, which is the false case when they're not married. Okay? And now let's say that I want to, for example, compute the probability that they are married given something else. Then what I basically have to do is, like, I have to compute this partition function when I'm, allowing them to be either married or unmarried, and the partition function when, for example, they're not allowed to be married, which would give me the probability that they are married. Okay. So why is this tractable, right? Where does the tractability come from? It just comes from the fact that the structure of the knowledge base is exactly parallel to the structure of the computation of the partition function. Okay? Every time you have a decomposition into parts, you have a product. Every time you go down the is part hierarchy, you have a product. Every time you have a decomposition into classes or subclasses, meaning you go down you go down the is a hierarchy, you have a sum. Okay? So if you have the knowledge base, computing any queries will just a matter of doing this upward pass, computing the sums and products where I have subclasses and subparts, and then I'm done. Okay? So it's very, very fast.
So then TML is basically an AND OR graph? I mean, is this kind of what this is?
TML is not, very good question. TML is not an AND OR graph because it's a sum product network, right? So AND OR graph would be the logical representation, right? But remember that we're doing here a probabilistic representation, right? An AND OR graph, and there is a correspondence between the two, but the correspondence is actually quite subtle because an AND OR graph doesn't necessarily turn into a tractable probabilistic model.
It reminds me a little bit of some of the work that Adnan Darwich has done.
Yeah.
Knowledge compilation with arithmetic circuits.
No, absolutely. So sum product networks, which is what I really have here, are a generalization of arithmetic circuits, right? There's also something that is very related, which is, Rena Dekter's, right? Which is actually even closer to AND OR graphs, right? And Adnan, has explored this extensively, right? There's like the correspondence between the logical forms and, but remember, this is not a logical form, right? This is actually a set of arithmetic computations, okay? So there's definitely very well understood relationships between these two. One way to think about this is that if you took this and somehow just turned it into a deterministic knowledge base, this would be what Adnan calls, negation normal form, which is exponentially more compact than, things like CNF and DNF that we're used to, yeah. More questions? Okay. So,
So the weights in this thing, there are weights on the relations. Are there also weights on those subparts, subclasses?
No. So the weights are in two places, right? If you look back to here, there's weights on the subclasses, and there's weights on the relations. And you may ask, why are there no weights on the subparts? Initially we had weights on the subparts, but then we realized that we didn't need them. Because if you want different subpart decompositions, then you just turn those into weights of the classes that correspond to those. So we could have weights here, but it would be redundant, right? It's basically doing the same job in two places.
So one other question then. So the big problem with MLNs is, of course, weight learning. And is it true that the relations, since they are independent, given the classes and parts, are the weights really log odds of the
Exactly. So again, we're going to get to that shortly, how we learn this. But one of the nice things about this is that if I know the hierarchy, then everything decomposes beautifully, and I can just do weight learning in closed form. So the whole problem of weight learning basically goes away as well.
Even for subclasses?
Even for subclass. No, again, remember, provided that I'm given them in the data. If I've not given, remember, if I don't know these subclasses, this is a generalization of learning a mixture model, right? So you can learn it using EM or something else, but it's going to be an optimization with multiple local optima and the usual problems. Although, I mean, we've actually done this, for things like SPNs with EM and whatnot, and, and we get things to work in some ways that are not immediately obvious, but we can do that as well. In what I'm going to show here, we actually just assume that the classes are known in the training data. All right, so,
So would I be able to express rules involving relations? For example, can I say something like, if X is married to Y, then we are likely to have a child?
Yes, exactly. But the question is how, right? So here's an important thing that is maybe not immediately apparent here, which is the following. You can give me any one rule of that form, and I can express it in this form. What I cannot necessarily express is an arbitrary structure of rules. But any one rule, what a rule basically does is connecting one property of an object or a pair of objects to another property, right? And how do I do that? I can do that by basically setting up two classes, one where the rule holds and one where the rule doesn't hold, right? And so very, very straightforward. Yeah. So TML is nice because it generalizes all these things that people know and love, like junction trees, which is what you use for probabilistic inference, some prior networks that we've mentioned already, but also things like probabilistic context-free grammars. One of the nice things about TML is that, although we have not actually done this end-to-end yet, you could potentially do everything from the syntactic parsing to the query answering in one representation. But also sort of like newer things like probabilistic inheritance hierarchies, right? As I already alluded to, you can actually have an inheritance hierarchy with the usual properties that people had in the logical case, but now with probabilities. Right? You have some probability that a bird flies, and then if it's a penguin, that probability goes down, and then maybe if it's Opus who has a helicopter, it goes back up again. Okay? And the classes where it doesn't change, I just don't have this rule there. Okay? So it's quite nice in that respect, and more things that I'm not going to go over here. So how do we learn the structure of a TML knowledge base? Well, if you have an ontology, right, even if it's a partial, noisy one, it's very good to leverage that. And this is, in fact, what we've done in the experiments that we'll see shortly. But if you don't have an ontology in principle, you can also learn this completely from scratch. We haven't done that yet. We'll see how hard or easy it is. But either way, right, starting from an existing ontology or not, then the structural learning essentially, or at least the method that we've come up with so far, essentially consists of alternating between two things. One of them is dividing the domain into subparts, or aggregating from the most atomic subparts. And then what we basically have is a collection of, for example, families, or a collection of people, or a collection of states, or a collection of neighborhoods. And then once I have such a collection, I can learn a model for it in the form of a class hierarchy. Okay? And I can alternate between doing these two things. Once I have the structure, of course, I can also learn parameters. And as we already mentioned, the nice thing is that if I know the classes and the subparts, then everything decomposes, and I can do closed form maximum likelihood learning. The weights are basically just log odds of counts, and life is good. And I can do something very nice and important, which is shrinkage. Right? Shrinkage is saying like, oh, your probability of, a doctor's probability of conducting a surgeon's probability of doing good, heart surgery is average towards the mean of the hospital that she works at, for example, and then the mean of the hospitals in that region and whatnot. And this is very important to have, reliable models, right? Otherwise, like the best and worst doctors surgeons will just be the ones that do few surgeries because they're going to be the outliers. And there's a very nice correspondence between this and default reasoning. So my model, again, for say Opus's probability of flying is going to be a shrinkage of his own probability and his class's probability and the superclass's probability and so on and so forth. Okay. And we can do this by shrinkage. We can also just do it by backoff, where it's all or none. So the usual things that people do, for example, in NLP. Where will the data for this come from? Well, luckily these days there are some information extraction projects, right? Like like the ones that people here do, that give you tons of data to learn these kinds of parameters. So for example, you can have like surface forms of, like for example, well, is this Albert Einstein or Dr. Einstein or Professor Albert or whatever, right? We can have a distribution of that from things like Wikipedia links, right? Because of how, these objects are referred to by their links in other pages. Things like birth years of people can be found in things like Yago and DBpedia, and like elevations of mountains, for example. Let's say one class that you have is the class of mountains, and you want to know their elevations, right? You have, in DBpedia, you can actually compile very quickly if you have the right infrastructure set up, which we do, the distribution over the elevations of mountains and so on and so forth. Okay, so once you have the structure, provided you have a large source of knowledge, you can do parameter learning very very nicely, very efficiently in closed form, in a very straightforward way. Okay, so here are the experiments that we've done so far. So we've built a TML knowledge base that represents a chunk of Wikipedia, based off of DBpedia. So the ontology that we started from was the DBpedia ontology, right? So we didn't have to invent it from scratch. We just had to kind of convert it to TML form. We were, so in this, in the experience that we've done so far, we have over 1 million objects and object pairs, which is either a lot or very little, depending on how you look at it. But, I don't think scaling it up to many more, at this level would be very different. Of course, it would involve some interesting computational issues. And then we again learned the parameters using things like, DBpedia and Wikiprep and whatnot. And in the experiments that we've done, we actually had over 1 billion parameters, which again, I think is a fairly respectable number of parameters to have, even by today's standards. And then we use this for a couple of important, sort of like standard important problems, one of which is entity linking, right? So the model here is that we would like to take all of these knowledge extraction projects and merge them all into one big ontology and one big knowledge base. Okay? So there's Yago and there's Wikipedia and there's Nell and and then et cetera, et cetera, et cetera. And what we would actually like to do is merge all of the information into one ontology, which of course is going to be noisy and uncertain, but that's what we can handle. So two experiments that we've done. One of them was linking Nell triples to DBpedia. Okay, so we've just built and populated our DBpedia ontology and learned parameters for it. But now I have let's say I want to take the information from Nell and absorb it, right? So I have something like Albert taught by Kleiner. Well, in DBpedia there's the Albert Einstein entity and the student of relation and the Alfred Kleiner entity and so on and so forth. And we would like to just add this into our TML knowledge base. And for that I have to be able to link these entities. Okay, and the way we do that, right, is for each triple in Nell, right, we go to these arguments, right, and we actually infer. This is actually a question that somebody asked before. It's like, who is this person most likely to be given the properties that I have for them, right? And then hopefully that will tell me that Albert here actually meant Albert Einstein and so on and so forth. Okay. We compare this to the the WikiLinks baseline, which is often used for this task. So this is this is something that took a bunch of people a lot of effort to produce, and we measure F1, and basically we do quite well. So here's what happens for various different types of relations, and what you see. So here's an F1 of 0.6 all the way to 0.9. So being further out is better. And notice that we're pretty much always further out, or equally further out, equally out. But the most, I think, salient fact of this is actually not just how much we do better or worse, because roughly speaking we do the same. Is that this was something that we did very quickly, right? We didn't have a big project to do this entity linking. It was basically just using what we had built up. And similarly, we've also looked, looked at linking, resolving entities between Yago and DBpedia, right? So you guys probably know all of these, projects as the competition, right? And Yago is another one which you're probably familiar with. So again, in Yago, there's Einstein. In DBpedia, there's Albert Einstein, et cetera, et cetera. We do the same process of running for each entity in Yago. We run the query in the tractable knowledge base that we built from DBpedia, and we have a probability that Einstein is Albert Einstein or some other Einstein. And then again, we compare this with the Perry system, which is a system that was built exactly for this purpose, and a lot of engineering went into it, and we beat it by a little bit. But again, I think the most salient fact is that this for us was largely a push button exercise. Although if you asked Matthias, he wouldn't call it a push button exercise, but I get to call it a push button exercise. And this is, so we have an implementation of this that's open source. It's called Alchemy Lite, right? Because Alchemy is Markov logic, and this is sort of like the light version of Markov logic, where your inference is always beautifully easy. The version that you can download from here is in memory, okay? However, what we have implemented, not completely, but enough to do the experiments, and that's what we use for the experiments, is using a database backend. So So using a database backend, what happens is that we do this all by evaluating queries on a relational database, on a MySQL database, right? We basically just roll things up. We do these joins. We compute the sums and products as we go along, and it's extremely efficient. You know, literally over the things that we've built up, we answer these queries in, you know, in seconds or a fraction of a second. Most of them in a fraction of a second. Okay. Of course, you know, truth in advertising, the kinds of attributes and dependencies that we have set up so far are not very complicated, right? But they're, you know, they already allow us to do some pretty interesting things. Now, here's a question that may be on the minds of some of you, which is, okay, this is all very nice, but at the end of the day, right, you will want to do things that do not fit into this form, right? And then you're back to intractability. What do you do in that case? Well, there are two things, I think, that you can do in that case. One of them is you actually do not need the whole TML knowledge base to be a consistent tractable whole. All that you need is that when you ask a particular query of that knowledge base and, you know, extract out, you know, do the knowledge-based model construction as it's called, and extract out the subset of the knowledge base that is relevant to answering that query, that inference be tractable. So I could actually have a very big messy knowledge base as a whole that never bothers me, provided that each query that I have to answer can be done in this way. Okay? So this in fact buys us something much, much more general than what we've seen so far. If that fails, and that may still fail, then there's another thing that you can do, which is now you can resort to approximate inference, as we do, for example, in Markov logic, right? You can do variational inference or belief propagation or MCMC. But for example, looking at the case of variational inference, right? What you do in variational inference is you approximate your intractable distribution with a tractable one, okay? And then, of course, you know, inference is easy, but you get some error, right? And now what we can do is we can use, you know, TML, or, you know, whatever version of this that you have, as the approximating class. And because the approximating class is much more powerful than, say, you know, in mean field, the approximating class is basically assuming that all your variables are independent, right? In things like, you know, tree-weighted propagation, it's assuming that basically what you have is a bunch of trees and so on. So those families are extremely restricted, meaning you incur a lot of error when you do the approximation. If you do this with something like TML as the approximating family, because the approximating family is much larger, you can get much closer to the real distribution. And we have not done this with TML yet, but we did do it with something like some Prada networks in this, you know, NIPS paper a few years ago. Okay? So there's definitely a lot more work to be done here, but I think in the long run, these two things are going to be very important. It's not just like, you know, TML is going to be, you know, allow you to do everything that you want in one fell swoop, because it's. But it's, I think, a very good basis for doing things like this. And again, you could argue that human beings do something like that, right? We have ontologies in our head. We decompose the world into parts and subparts. A lot of the time, we're exploiting this. And then when we're not, we're doing some approximation that takes advantage of what was already there. Okay? So that was the first part of the talk, and the longer one. Do people have any short questions? I mean, we can, you know, again, we can have more questions at the end. But before I go on to symmetry-based semantic parsing, any questions about this part?
Yes, at some point you mentioned billions of parameters.
Mm-hmm. A billion?
Of parameters.
Mm-hmm.
Yeah, and normally in MLN, I wouldn't even consider anything beyond 100,000, something like that.
Well, yeah, but this is why TML is good, right?
It's not, yeah, okay.
You have to remember that actually in an MLN, and in some MLNs that we learn, you could actually have a very large number of parameters, right? Because you can actually have parameters not just for the formula as a whole, but for the different instances of different arguments of the formulas, right? We have this plus notation that says, oh, I want to learn a different parameter for every state, okay? So MLNs could actually, in principle, have, you know, gazillions of parameters. In practice, the MLNs that we learned, some of them had a large number of parameters, but not a billion, right? I mean, because even the parameter learning, you know, would be hard because of the optimization, and in fact, the inference is embedded in it, and so on and so forth. But here, in this setup, we can actually do this, you know. And we got a billion because that's what we needed in this case. You know, if it had to be 10 billion with, you know, or more with the necessary parallelization, there's no reason why it couldn't work.
And there's no overfitting happening here with billions of parameters.
Oh, I mean, you have to guard against overfitting the same way that you always do. But remember, the basic mechanism by which you can combat overfitting here is the shrinkage, right? Is that I can learn a model for, and this is what we do. Like, we have a model for Arnold Schwarzenegger, We have a model for actor. We have a model for person, right? And then what happened is that, well, the parameters for Arnold may be very overfit, but I'm going to shrink them towards the parameters, right? So the way you control overfitting is by deciding how much you shrink. Okay? So in a way, what we're doing there is not too different from the standard things that people do, but it is in sort of like this relational world, which, you know, is more general than what people had before.
So I attended UAI 97, and one of the talks title was Object-Oriented Bayesian Network.
Oh, yes.
And the starting sentence in the presentation is, you take two buzzwords as you throw together and you have a good paper.
I know the authors of that paper. I don't think they would like that characterization, but okay, keep going.
So my question is, why the name Markov logic?
Oh, your question wasn't expected given the preamble. Well, remember, this is a tractable version of this is a tractable subset of Markov logic, right? So in a way, what we're doing here is we're following the same path that classic AI followed, right? First of all, people figured out, hey, we want to use first-order logic, and then Robinson figured out how to do resolution, right? And this was nice, and we actually have the exact, so the equivalent, the generalization of first-order logic is Markov logic because it's logic with probabilities, and then the equivalent of you know, Robinson's work is probabilistic theorem proving, which we developed a few years ago, which is a probabilistic generalization of theorem proving, right? But then what people have spent the last 40 years doing is coming up with tractable subsets of first-order logic, like, you know, default logics and, you know, Hard-clause logic and whatnot, because that's actually what you can do things with at the end of the day. And so what we're trying to do here is the exact analog of that. We're trying to come up with subsets of Markov logic that are tractable. And, you know, TML is actually just one. We've developed a few others by now, and, you know, and there'll be more in the future. The question I thought you were going to ask, because people sometimes ask, is that, like, well, didn't people do this almost 20 years ago? You have to remember that when people did that, the languages that they came up with were intractable. So this started out with tractable relational languages, but when they made them probabilistic, they became intractable, which you could argue negates the purpose. But given what they knew back then, there was nothing better that they could do. The important thing here is that, like, yes, this is an object-oriented representation language, but it is tractable. It is the first tractable probabilistic object-oriented representation language. Somebody else had a question?
So I'm going to ask a less answerable question, which is going to like equations and handling and stuff. But it feels to me like you said there's this trade-off between expressivity and tractability. And I feel like that trade-off is balanced in terms of the structure of the network, in particular like depth and boundary factor. Okay, so can you like wave your hands and say what your ideal network would look like? In what case does this look quite good in terms of this?
Well, I mean, it depends, right? So TML does not commit you to a particular type of class hierarchy, right? Okay, you could have something that's very shallow and wide, or something that's very tall.
If it's very shallow and wide, then, you know, tractability goes out the window, right?
No, actually it doesn't. I mean, it's entirely up to you, right? You know, think of this as, say you want to build something more for a specific domain, right? Then it'll be narrow, but it might be deep. Right? If you have just a generic common sense knowledge base, it'll probably be shallow and wide. But what we'd really like to have at the end of the day is something that is both wide and deep. Right? It's all of the world, it's all of the knowledge of some particular, you know, right? All put together into one big structure. Right? And there's nothing here that forbids that from happening.
So why do you think it's just big? Like if it's like super shallow, there's just like one top object and then everything out under that, then it doesn't feel like you're very, as you said before, it's like not very tractable.
No, well, it's tractable, you know. Here's what happens. If all I have is this is a good example, right? Let's suppose that all I just have is a naive-Bayes model of the world, right? I have a distribution over possible, you know, clusters that the world could be in, right? And, you know, I could actually take DBP and turn it into something like that, right? The problem is that one of two things. It would either be very impoverished, right? So when answering queries like, for example, you know, who is Albert? You would get a lot of wrong answers, right? Or you would need a very large number of components in that model. Right, that naive-Bayes model for the world, right, would need a, you know, if you allow me an infinite number of components for the top object, then I don't need a deep hierarchy, right? The whole point, however, of having depth is that, and it's the same thing with some product networks, is that a linear increase in depth actually buys you an exponential increase in the effective number of mixture components. So it's actually very powerful. Whether you will need it or not in practice, you know, is another question. But the fact that you can do that is very powerful.
But I guess this sort of comes back to my previous question about, I never really understood your answer about saying, can you say is the mother of the Smiths also working for Microsoft? And it seems as soon as you build in this depth.
Oh, well, okay, so let's look at that example, right? I could have, so let's take the brute force version, right? Is, well, there's the world, right, in which she does, and one in which, you know, the mother of Smith works for Microsoft, and one where she doesn't, right? And I could have that represented at the top level, but it would have to be represented along with the answers to the same questions for everybody else. So what I want to do is I want to push that down to some subset of the world, right, which is maybe Seattle, right? I know that she lives in Seattle, right? And now I'm only doing for those people, and now that gets multiplied by an independent something for another Anna that lives in LA, right? And this is where I get an exponential improvement in the size of the
You're
tier.
saying that the Smiths are a subpart of Seattle as opposed to a subpart of families.
No, yeah, it's up to you, right? So you have to make a decision, right, as to how you break the world up. And that decision will involve some compromises. You could say the primary way in which I'm going to divide up the world is geographic. I'm going to first divide up the world into continents and countries and states and regions and cities. Let me just give you, so this is a newer idea, right, one that's much less far along, but let's see if I can convey just the basic idea in 6.5 minutes. So here's another aspect of the problem of extracting knowledge from text, right, is that I'm starting out with sentences and I need to map them to logical formulas, right? And this is the semantic parsing problem, another one which, you know, you're very familiar. And, you know, and then once I do that, I can answer questions and I can have a natural language interface and so on and so forth, okay? And you can look at this as a structured prediction problem, right? My input is a sentence and my output is a structure, except that the structure, instead of being, say, a parse tree, is actually a logical formula. Very nice, and, you know, people like Luc Zettelmoyer and Ray Mooney and whatnot have made a lot of hay with this, but there are two very big problems with this. The first problem is that no one can agree on what the formal representation should be, right? What should be that magical internal representation, right? I can say it's TML, and you can say it's something else, and no one is ever going to agree on this. And you could even argue that if you choose one, you know, you've already thrown out the baby with the bathwater, because the power of human reasoning is that you can, you know, switch between representations and whatnot. So this is the first problem. But let's suppose that we had actually solved this problem, okay? Now you have another, I think, even bigger problem in some ways, which is, where are you going to get the labeled data? Who's going to give you pairs of sentences and their logical forms? You can't, you know, outsource this to Turkers, right? You can say, you know, turn this sentence into first-order logic. Right? And, you know, and therefore, you know, this can be done on a small scale, but it cannot be done on a large scale. We need a way to do semantic parsing that will work on, you know, something very large, right? As large as our, you know, as our cloud can handle. So what I would like to just briefly describe here, and by the way, if you want more details, we have well, actually, we have a paper in the semantic parsing workshop this summer, but I guess the paper did not appear. So if you, you know, if you want more details, you know, I can send you the actual paper that we submitted. We chose not to actually publish it because these days, you know, if a paper is published in a workshop, the conference might not take it and whatnot. So what's the idea? Well, let me digress to something that might seem at first completely different. How many people here, just very quickly, are familiar with symmetry group theory? Okay, that's actually a few of you. So hopefully, what I'm going to do here in the next, you know, 5 minutes or even less is a very, you know, quick introduction to symmetry group theory, and then we'll see why, and then we'll see how we're proposing to actually solve, you know, these two problems by using symmetry group theory. So what is symmetry in geometry, which is how it's usually first introduced? The symmetry of an object is a transformation that maps it to itself. So for example, a square, you know, has the following symmetries: rotations of 0, 90, 180 into 70 degrees, right? Because if I rotate it 90 degrees, it's the same square again, and so forth. Reflections on these axes that I've shown here. And then here are some important properties, right? The symmetries can be composed, and when I compose them, I get another symmetry. So if I rotate 90 degrees and then 180, basically I've rotated to 70 degrees, right? And if I compose two reflections, it's equivalent to a rotation and so forth. And there's an identity transformation which is rotating by 0 degrees, right? That leaves the object unchanged. And then each symmetry has an inverse, right? Rotating 90 degrees, the inverse is rotating by minus 90, and so on and so forth. And the composition of symmetries is associative, okay? And so what this means is that symmetries satisfy the group axioms, right? What is a group is a set and a binary operation with 4 properties: closure, identity, inverses, and associativity, right? Things that we know and love, like the real numbers with addition form a group, right? Lots of things in mathematics are groups. But the interesting thing about symmetry groups, right, is that the group elements are actually not objects. The group elements are functions, which makes it much more powerful. And the group operation is function composition. Okay? So if my symmetries form a group, then I can compose them, and I know that I have these properties, and then there's a lot of theorems and nice things that follow from it. Okay? Most people who are familiar with symmetry group theory, what they know, although it's not that relevant to us here, is what are called Lie groups. They're continuous symmetry groups, like, for example, the symmetries of a circle, right? I can rotate through any degree, reflect on any diameter. And then there's things like the symmetries of Euclidean space, like translations, rotations, and reflections. And what do these do? They preserve the distance between any pair of points. Okay? And symmetry group theory is extraordinarily widely used in mathematics and physics and fields like optimization and search and even things like model checking, vision, machine learning. Poincaré basically said that mathematics reduces to symmetry group theory. Phil Anderson, a physics Nobel laureate, says that physics is basically the study of symmetry. So this is pretty powerful stuff, right? Essentially, all the laws of physics just follow from a bunch of symmetries of the world. It's quite amazing. In things like optimization and model checking, you can take advantage of symmetry to reduce your search space. So you want to play tic-tac-toe, right? If you notice the symmetries of the board, then once you solve things for one, you've solved it for all the symmetries and so forth. It's also used in vision, in machine learning, in lifted probabilistic inference, which is where I first got interested in it, right? When we have these large relational models, you often have many chunks of the model that are exactly the same, which means that there are these permutation symmetries under which, for example, the partition function stays the same, and we can take advantage of it there. So there's actually a very active area of research now is using symmetry group theory for lifted probabilistic inference. But what I would like to propose here is applying it to the problem of semantic parsing. And the way I would like to apply it is the following. Let us define a symmetry of a sentence as a syntactic transformation that preserves its meaning. Because another thing that is not changing is the meaning of the sentence. Right? This is the invariant that we're interested in. And when I say syntactic transformation, it could be lexical. It's really any periphrastic transformation. Any change to the sentence that doesn't change its meaning is a symmetry, right? And then they can be composed, right? If one thing preserves the meaning and then another one does too, then the composition of the two still does. So, synonyms, paraphrases, active-passive transformations, composition of two sentences into one, using and whatnot, these are all symmetries. Like, for example, if I have something like Bill wore shades, William donned sunglasses, sunglasses were done by William, right? If I can recognize these symmetries, like, for example, shades to sunglasses and donned to were done, I can answer a question like, were shades donned by Bill? Which is something that was actually never said, right? And there's actually no single paraphrase that gets you from one of these to these, but composing them does, okay? So then we can define the meaning of the sentence as the following, right? We need a notion from group theory here, which is the notion of the orbit of an object under a symmetry group. The orbit of an object under a symmetry group is the set of all objects that it can be mapped to by symmetries in the group. Okay? And so what we do is we define the meaning of a sentence as its orbit under the symmetry group of the language. Okay? And orbits have a number of interesting properties that are very advantageous for us in terms of learning and inference. One of them is that the orbits, these are like known, symmetry group theory things, like, and most of them are easy to prove. The orbits of the objects in a set partition the set, and so on and so forth. So what's going to happen, right, is that there's going to be a one-to-one correspondence between the orbits of the sentences and their meanings. And notice that, and basically to kind of like look forward a little bit, the semantic parse of a sentence is really just going to be figuring out what its orbit is. And once we know its orbit, we're done. Notice that this means that the meaning need never be explicitly represented. We don't need to make that choice of the formal representation language. The formal representation language is left implicit. Once you have your structure of orbits, you could say, well, now I'm going to express this in first-order logic if you feel like it, but you don't have to. You don't have a representation language, imposed a priori. And the orbits, of course, can have compositional structure, right? And we know how to do these things. We can have products, we can have sums, and we can build up orbits that way. I can replace one word by a synonym, another word by a synonym. I can have an active-passive transformation, and then within that I can have these transformations for the synonyms for the individual words and whatnot. And I can put probability distributions on these orbits. Okay. So what I'm going to, in essence, the language is going to become a very big mixture model where each mixer component is the meanings of one sentence, and then I have a model of the ways in which that sentence could be said. But these things, of course, all share a lot of structure. All the different ways of saying Barack Obama, right, will be reused in all the different sentences that involve Barack Obama and so forth. So, in symmetry-based semantic parsing, as we call it, the goal is to find the most probable orbit of a sentence. Because if I found that, now I know what the meaning is, and I can answer, for example, the question, is this true or not? So what effectively, what our inference process is going to do is map my unknown new sentence to known sentences by composing symmetries. If I can do that, then this is a sentence that is not equivalent to anything that I've seen before, and what I have is a new orbit under the symmetry group of the language. Okay? And as I already alluded to, we can do this efficiently if we take advantage, or if we assume a compositional structure to the orbits, which, in natural language is, of course, a very natural thing to do. And one way to think about this is that this is going to be very similar to inference in, guess what, sum product networks, where a union of orbits, leads to a sum of probabilities, and a Cartesian product of orbits, leads to a product of probabilities. And of course, I'm glossing over the details here, over many details, but I'm just trying to give the basic idea. So now, what is learning, right? What does it mean to learn a symmetry-based semantic parser? It's just to discover the symmetry group of the language. Okay? English has a symmetry group. French has a symmetry group, right? And all I'm trying to do is discover that group, possibly one symmetry at a time, right? And then they compose on all those good things, and I get a lot of power out of that. Okay? And now my data can just be pairs of sentences with the same meaning. It doesn't have to be pairs of sentence and logical form. This is not, and there are large databases of paraphrases out there. We can swallow them all up, and we're doing that. Or you can ask your Mechanical Turkers, please restate this sentence in your own words, and that's training data. Or even say, tell me if these two sentences mean the same or not. So large amounts of data are now very easy to come by, right? So this solves the second, or at least it's a much better solution to the second problem than labeling sentences with logical forms by hand. Okay. Now the structure of what we're trying to learn, notice, is not just a big pile of symmetries, right? There's this notion in symmetry group theory of a generating set, which is a set of symmetries from which, by composition and inversion, you can create all the others. And this is really what we're trying to discover, is some sort of like minimal generating set, such that by composing things from that generating set, we can get all the varieties of ways in which things can be expressed. Okay? And then the parameters are going to be the orbit probabilities. My initial state can be my known symmetries, right? I don't have to start from scratch. I can actually write down some things that are within our symmetries and start from that. And then my operators can be things like filling in gaps in derivations, right? Like, for example, I could map this to this except for this gap. Let me hypothesize. And if this gap occurs in a lot of these pairs of paraphrases, I can hypothesize that there's a symmetry there. And my score function can be the usual type of thing, like penalized likelihoods and so on. We've done some very preliminary experiments with this that, in the interest of time, I'll just skip over. Let me just conclude with one question. So how does this all come together? Right? Maybe this is a nice approach to semantic parsing, but usually the reason people get logical formulas, right, out of sentences is that then they want to do logical reasoning with them, right? They want to chain them and whatnot. And does this actually give us the power to do that? Well, this now is speculation, right? This is not something that we have not done yet. But here's the way in which potentially we can put this all together, which is to notice that logical inference rules themselves are symmetries of knowledge bases. Because what applying a logical inference rule does is add a sentence to a knowledge base without changing the meaning of the knowledge base in a very, formally well-defined way, right? The set of models of the knowledge base remains the same. For example, if you do modus ponens. So if I have a knowledge base that says Socrates is a human and all humans are mortal, and I apply modus ponens to it, now I have this knowledge base, okay? So this is a syntactic transformation of the knowledge base. The two are different. But the meaning hasn't changed, okay? So in a way, we can actually fold the inference process itself into this, general idea of symmetry-based semantics, okay? So to summarize, we want to extract large knowledge bases from text and reason with them. One thing we need for that is a tractable representation that is both relational and probabilistic, because text is rich and messy. One solution for that I've described here is tractable Markov logic. We also need to be able to transform the raw text sentences into some formal representation with very little supervision, okay? Or at least, supervision into the traditional sense. And one potential solution to that is symmetry-based semantic parsing. And of course, we're working on these things, so expect to see more developments over the coming months and years. Thank you.